Great. Welcome, everyone. I'm Julia Pollack. I'm the current artist and curator for the Carl R. Woese Institute for Genomics Art of Science program. We're an interdisciplinary science research institute that not only does work on genomics, but we also do work to translate that information back to the public. So will you please introduce yourself and tell us a little bit about what you do at the IGB?
Oh, hi. My name is Xudong Guan. I'm the MR specialist at IGB core facility. In here, we mainly provide a microscope service for the researchers in and out of campus. I'm mainly working on NMR, AFM, and micro-CT, generally doing instrument maintenance and user training. Sometimes we run sample for the user as needed.
Awesome. So will you tell us a little bit about the process of imaging the specific fish specimen that is on display in the water piece?
Okay, so it's all start with a conversation with the user. So Chris emailed us about he want to use microCT to record this fish sample, and we have a conversation, talk about what he need from the image, what we can do, what kind of resolution we can provide. Also, we look through the sample so that we have an idea of what's the size of this, what's the shape of it. That's pretty important for the CT scan. After that, so he provided us a sample, and when we have the sample, the first thing we need to have a fixture so that we can hold the sample still on the stage to do the image of work. Also, in this case, we need to have the fish in the water.
Mhm.
So we construct this container from acrylic so that it fits the size of the fish. We have different size of tubing, so we can construct different size of container if needed.
Cool.
So that we have water there, we have fish in there, then we can put it on the stage so it's not moving around. Then we can get a good image from there. After we have the sample positioned well, we need to get the sample centered. The idea of getting a sample centered is that we want to use as much of the detector as we can, so that we want the sample be in the center of the stage. So the left side has part of sample, the right side of detector detect part of sample. In this case, we use a full detector. After all the, we design and construct a micro adjuster. So we are capable of center sample in scale of 1,000th of the inch, so that it will give us the best result from there. After that, we need to optimize the X-ray. So basically, we will adjust the voltage and microamp, so that the X-ray can penetrate the sample. At the same time, it's not saturate the detector. Basically, we want X-ray to penetrate the sample. We also want to maximize the contrast in the sample, so that we can see things clear. After getting that set up, we adjust the distance between the sample and the source, and the detector and the source. With distance determined, then we know the magnification, what kind of magnification we can have, what kind of resolution we can have of the sample. After that, we set up the scan. So basically, we have X-ray penetrate through sample, reach the detector, then we record the image, we call it projection. Then we rotate the sample with a small angle, then we take another shot, we get another projection. Generally, we have around 2,000 projections for each of those CT scans. So with all those 2,000 projections we collected, afterwards, we are going to do the correction and geometry. The correction is about the detector. So we want the detector to have a uniform intensity and to remove the background, the noise, and remove some dead pixels from the detector so that we have a clean image finally. After the correction, we do geometry, which normally we have geometry too. So this is one of those, but we have multiple at different sizes. Over here, we have a series of iron beads here, a small metal ball. We know the size of the ball, we know the distance of each ball from one another. So we put it on stage, we rotate it. So we kind of generate a 3D coordinates,
Mm.
which our sample will be falling in. Then we are going to know the size of the sample, all the informations. After we collect all the geometry, we collect all the projections, we put it in software, we do 3D reconstruction. Then we generate a 3D image of this, this fish sample. We not only generate a 3D image, we have of the sample, we have both inside and out. We don't just see the surface of the sample, we also see all the skeleton inside there. We also see the muscles of the fish inside. So that's kind of the whole process of the imaging.
That's incredible. Thank you so much for sharing. It's so cool to see that you have to even make a specific kind of container to have the sample held in, like having to fix something that's the right side for the sample. That's so wild.
Yeah. So it's not just the size. It's also need to be low intensity, which means it's transparent for the X-ray.
Mm,
You don't want to have something block a lot of X-ray there. You want X-ray to penetrate your sample, not whatever you use to support your samples. So that's another thing. So that's why we choose this acrylic tubing here.
it seems like such an incredible process too, because the samples, right, are suspended in a liquid, and you
Yeah.
always think of a microscope, oh, you put something fixed or something like that can stay in one position. So it's interesting to have it sort of be in liquid while you're imaging.
Oh yeah, this is a specific sample. It's not like we run all those samples in
Yeah,
liquid, but this one we have to run it in liquid.
cool. Can you say anything about the importance of CT scanning or this kind of imaging?
So the advantage of CT scanning is that there's several advantages. One of those is we can see through the sample. We don't just see the surface, we see the inside. And normally when we do imaging, we image the slides,
Mm,
which means a thin layer of sample, or sometimes the surface of sample. But for the CT, we image the whole sample.
mm,
We can see the whole sample, we can see outside, inside, everything. After we have a 3D image reconstructed, we can slice it digitally instead of physically. So we can slice at any angle we want, and we see how it looks like on this orientation. If it's not a good choice, we change the orientation. We can slice it again. It's not like you sample physically. If you slice it, you say, wow, it's not an ideal angle. Well, it's done. You cannot put it back,
yeah.
right? So, and whatever we do with digital slides, we don't lose our sample. We can still have the sample, give sample back to user. User can do any other research with it. And also, you can share this information online, like what Chris want to do. If they want to upload the file to the server so that people from distance can see the fish. They don't need to see the real fish, right? They don't need to come here. They don't need to send the fish to them. Even you have the fish, you only see the outside. You only see the surface. You don't see the skeleton of the fish. So that's kind of the advantage of this technique.
That's awesome. Yeah, I was really thinking about in this process how cool it is to be able to preserve the specimen so completely, but then be able to see so many layers of data inside of it. It's just amazing.
Yeah, yeah. It's depending on what you want to see. Which part you want to see, you can slicing over there and see how it's changed with space.
That's excellent. Thank you so much. I really appreciate your detailed explanation. It really made things clear for me. Thank you very much.
Oh, thank you.
Have a good day.
You too.